typical airport is a constantly changing dynamic environment full of passengers and airport workers ensuring that flights take off and land successfully. Many human operators are involved with repetitive tasks such as moving heavy and fragile cargo as well as luggage. This may lead to a failure of perceiving the critical aspects of their immediate surroundings. Our team of 5 students and 2 advisors have worked on a technical solution to this. Referencing companies such as Waymo and Kodiak Robotics, the team acquired an existing electric car platform to convert into an autonomous cargo transporter.
The short clip here demonstrates how our purchased car is originally operated. As you can see, there is some trigger at a handlebar position for longitudinal speed control, and the steering is achieved by the manual turning of the human operator. We installed sensors with their supportive structures. We built Arduino-based actuators, including a self-fabricated linear actuator steering mechanism and a reverse-engineered digital propulsion control. We also put onboard batteries to power all of them and the computer. Here is the result for the hardware testing. On the left is how Nathan smoothly maneuvered the cart with the joystick in the parking lot. On the right is the mapping data the LiDAR collected with the ride.
The software stack that was designed to autonomously operate the cart was comprised of 3 main functional areas. An Ouster 64-line LiDAR was chosen for the mapping and localization, as we can get a high-resolution point cloud map. Through use of an algorithm called LEGOLOM, the distance accuracy of mapping was 97.6%. A Kalman filter was used to estimate the state of the moving object of interest with noisy measurement.
In terms of path planning, a predefined continuous global path was manually selected that avoided all static obstacles. Due to dynamic obstacles, a path follower was necessary to ensure that the cart stayed close to the predefined waypoints and velocity. We used model predictive control to track a path reference, which iteratively solves a constrained finite time optimal control problem in closed loop with the localization module. This outputs the optimal steering and velocity control inputs to the low-level control.
The low-level control implemented a feed-forward PI controller to achieve the closed-loop velocity control. Closed-loop steering control was also implemented using the custom-built actuator steering system. This visualization represents both the localization and path-following packages working simultaneously. A simple vehicle with wheels was plotted, and its progress following the predefined black waypoints through the point cloud map can be observed. The model predictive control maintains the vehicle position, velocity, and heading angle close to the reference values. This software stack was ready for deployment on the electric cart.
The team has learned a lot throughout the development of this technical solution. If given the time and facilities, we would continue fine-tuning the low-level control and high-level software, as well as test the full software-to-hardware autonomous stack. There were several people and facilities that helped the team, including the UC Berkeley Echeverry Machine Shop and the NPC Lab. The team would especially like to thank our advisors, Xu Shan and Professor Francesco Borelli, for their guidance throughout the project.